You guys have heard of forces? You guys know gravity? The force for gravity? Yes. A force is actually a push or a pull. So I can push this, I'm applying force on this, and pulling it. Do you guys know what an area is? Yes. Okay, area is something that's two-dimensional, right? Is that that? Okay. Do you guys know what units are?
Yeah.
You guys know units? Okay, so the unit of force is number of newtons. We usually shorten that by just putting the capitalized N, okay? And the for area is meters squared. So the unit for pressure is numbers of Newton over meters squared, which is equal to 1 Pascal. Or for short, we put 1 with the capitalized P and the lowercase a. Okay? So now that we talked about area, do you guys know what a 1 meter box to 1 meter box is? Do you know what that is?
I do.
Do you know how much that is?
40?
It's actually just 1 meter. 1 meter squared.
Oh.
Remember room 17? We did that just a week ago, right?
Yeah.
Okay, so would that make a 2 meter by 2 meter box twice as big? Is it twice as big as the 1 meter?
Yeah.
It's actually not. It's actually 4 meters squared. It's a lot more.
Oh, I think it's 2.
Okay? Do you guys know the area of a circle?
We haven't learned
Pi.
that
You
yet.
guys ever learned that?
No.
Pi. Well, pi is part of it, yes. Well, area of a circle is pi r squared. The r is the radius. It's from the middle to the circumference. If you guys do learn that. Okay, so
It's air pressure is a force over an area, but the force that's being applied is the air. So you know there's air surrounding all of you at all times, and I use this to the students to kind of get them to understand. I ask, have any of you guys swim to the bottom of the deep end of the pool? And then some of them say yes, some of them say no. And the ones that do say yes, I ask them, well, where do you feel, where does it hurt at? And they answer with the ears. And so I ask them if they can feel any pressure anywhere else around them. And they usually respond yes everywhere. And so what I get them to do that first so that I can show them that the air pressure that's being exerted on us at all times is equivalent to 15 pounds every square inch. And so there's 15 pounds every square inch, and depending on how your body size, that's a lot of pounds of air that's being pushed on you. And so next I'll ask them, why aren't you imploding on yourself? Why is it that your body's going to keep the same form that it does? And the reason for that is because we breathe in oxygen, we have bones, we have muscles, we have liquids in our body that actually counteract that force.
Momentum is a very simple concept, but it's one of those things that you just have to know if you're going to do anything with Newtonian physics at all. And depending on the age group, you would write it as mass times velocity or mass times speed. Velocity for higher level. Technically, it's mass times velocity. I'm assuming everyone here knows the difference between speed and velocity. All right, that's good. If not, the velocity is just speed that has a direction. Speed is just you're moving, you don't know where. Now, an easy way to get this ingrained into a student's head is to go demos. Ask them like, which would you rather play dodgeball with, a regular dodgeball or a bowling ball? And so, if they're sane, they'll say regular dodgeball, and that's because bowling ball has way more mass. And then you go into the difference. There's a lot of you can do. Do you want your car to get hit by a fly or a truck? Then you go into the difference between mass and weight. And you ask, I have a 1 kilogram brick here, it's a mass. If I were to drop this here on Earth, would it hit pretty hard? And most would say yes. And then ask if you went to the moon and dropped this, would it still hit pretty hard? Depending on the age group, most would still say yes. And then you note that weight is a force due to gravity, whereas mass is just how much stuff there is in a object. This has 1 kilogram of stuff. Its weight is actually about 10 newtons. On the moon, it would be about a sixth of that. Conservation. And this time it's rotational. Momentum. So usually what I'll do is I'll start the equation and then I'll just do a little, rotational, and then as we get to each one of them through the process, we'll fill in the blanks, the equations. So right now I'll just throw a time sign in right between them. I'm doing it vertically. And it'd be great if I could have 2 volunteers to come up.
Give an idea what they're gonna do. Are they gonna just spin the baton?
Yeah,
They
you
don't have to
guys
stand
are
on
just
your head.
gonna spin a baton like this. It's nothing scary.
And that's one thing, important thing to do, guys, when you ask for volunteers, right? Give them an idea what they gotta do, right? Otherwise, they're going, what the heck am I going up there for? Yeah. There's one, where's the other one? There you go. And this is something you
Okay,
really have to
fantastic,
feel, guys.
awesome.
You have to feel
All
it.
right. Now, these are the same height, correct? You want to show everyone that it's not rigged right off the bat. It's actually rigged, but right off the bat.
Come on now, no rig, you don't talk about rigging.
But, so they're the same height. Feel them. They weigh about the same amount. They do weigh the same amount, in fact. You can feel them. They weigh the same amount. Okay, now grab it in the center. In the center right there on the tape. Grab it on the tape. Okay, now stand and turn. And what you're going to do is stick your arm out and just rock it back and forth as fast as you can.
Like her, yeah, fast like her.
Yeah, no, go faster. Just go faster. Faster, keep up with her. You know what? Okay. Okay, yeah, wow. Okay. I haven't seen that amount of difference. Now let's give it another shot. Okay, go. Let's see what it's like this time. Okay. A little bit faster.
Try your right arm.
Yeah, try your right arm up here. Yeah, right hand. There you go.
There you go.
Okay. Well, she's not beating you like crazy.
Right, we learned something there, didn't
But
we?
you are
Yeah.
going faster. You're going faster than you were, and you're going a whole lot slower. Is that harder to do?
Yeah, it is.
Okay, now see, why is that? Why would 2 pieces of metal that are the same length and weigh the same amount be harder to turn?
So which one was hard? The red one, right? The red one was hard?
Yeah, this
The
one's
red one, right?
harder.
There's the red one.
Now, if you look at them, you can tell a slight difference, and that's these 2
Yeah.
little couplings right there. That is where the mass is located on the axis. So with this, we want to talk about a little bit of axis of rotation. So if you're turning it like this, which way is my axis of rotation? Can you take a guess?
Middle?
Yeah, it's in the middle. It's sticking out. So when I'm rotating like this, it's a horizontal axis of rotation. Good thing to do with kids is have them move their arm like this, and vertical axis of rotation. Their arms like this, horizontal. You can use a door. The door swinging is a vertical axis of rotation. So that they get that idea that something, when it's rotating, is rotating around an axis. And now to show you, I lost my word.
No, the other one.
Now to show you,
Good turn both on.
if this is
The other one, there we go. There we
if
go.
this is conserved, if the rotational momentum is conserved, that means that means these.
Yeah, Evan does that sometimes. He'll leave you hanging.
Yeah, I'll leave you
Have a
hanging.
seat, have a seat.
I'll just have a whole group up here just saying one round. But so that means this whole part right here always has to stay the same. So it has if this one goes up, the other one has to go down. It has an inverse relationship. And it's speed times inertia So what we know from trying it out is that the speed was different. So the one with the red, the speed was lower, which just through this equation you can tell that the inertia is higher. The inertia is actually
the mass times the distance squared. So distance is actually more important than the mass itself, but that's kind of getting into, you know, a little
High
bit,
school level, yeah.
yeah, a little bit higher level.
Yeah.
But you can have a lot of fun with these with younger kids. You know, they really enjoy just spinning them. They enjoy feeling the difference between one and the other, which you can tell. You know, it was there's quite a big difference in the amount of effort you have to put in.
So, as everyone's saying, usually bring out the chair at this time. And first we want to establish that the kids understand what axis of rotation is. So first we spin the chair and say, where's the axis of rotation? You know, it's along here, right? Down the center of the chair or stool. And that's a vertical axis of rotation. And then the next thing we do, you know, we bring up the ice skater thing, the analogy. And then we talk about how we hold these weights out here. If I'm spinning around like, you know, like a crazy person, if the weights are out here, do I have a higher rotational inertia out here, or do I have a higher rotational inertia in here? You know, and usually the quicker kids are the ones that say, oh, like out here, you're gonna have it much higher. So now I'm gonna be on the stool here, and then you know, safety first. You tell them to make sure that their feet are on this this bar right here when we spin them. So we do give them a little bit of speed and just bring them in.
Bailed out, didn't you?
And also another thing that I failed to do was if you bring them back out, you slow down again. You know, because it's conserved throughout the whole time. And once you're dizzy, you can spin the other way and it goes away.
And this one's actually pretty easy to demonstrate, even if you don't have like any like props, like you don't need like a bed of nails or something crazy to do it. Like you can use a door and stuff, and I'll show you how you guys can do that. So a torque is actually, it's the equation for this is force times lever arm, and we're going to use a wrench to demonstrate it. But actually we have the wrench out, so I won't go. So you guys heard about force in the first one. It's like a push or a pull. You guys are pretty familiar with what a force is. So now if we apply that force at the end of a lever arm, it's going to cause like a rotational motion. So we can apply more torque by either increasing the force that we apply to something like a wrench, or by increasing the lever arm, like where we apply the force, like in relation to the axis of rotation. So we're going to use a wrench to do that here, but actually another way to do it is, you know, you can have kids try to open a door by pushing on like where like the doorknob is, and it's pretty easy. Then have them push like right next to like where the hinge is, and it's going to be a lot harder. So if you apply this, you know, you're going to have to apply a lot bigger force if you try to open a door close to the hinge, close to the axis of rotation. Then if you if you give yourself a bigger lever arm, so go farther out from the hinge, you can apply a smaller force, and you're going to get, you know, the same amount of torque.
Right. So that's the concept that we use the wrench for. And so the first thing, we do this after rotational momentum because it ties in really closely with that. And so the first thing I'll do is ask them, where's the axis of rotation if I'm trying to loosen this pipe in? And it's horizontal, right? Because it's going to go in a circle around this axis. And so then talk about, okay, well, if I'm pulling on, do you want to pull here or here? And you want to pull here, right? Because you have a longer lever arm. So it's farther distance from the pipe fitting to where you're applying the force. And then you can get more technical and talk about how the force needs to be perpendicular and different things like that for high school levels. But for lower levels, it's just fun to show them the idea, and then you get a volunteer. And I don't know if it's tightened or not right now, so I can actually do it. But then you have volunteer, and it's fun in like a high school class setting because sometimes you see like the big boy in the back of the class who's like, I got it, and they come and he pulls really hard, and then they can't get it. And so we're like, okay, so what can we do if we're going to use the same kid? We want him to loosen this. How can we change it? How can we make him apply more torque? Because torque is what we need to loosen this. And so then we say, well, the only other thing, we kind of hint towards it, right? Lever arm. And so then what we do is we get these pipes, right? And we say, okay, so with that idea in mind, how can we use this to help us? And so some kids will say, like, maybe you can whack it. Okay, well, we don't want to do that. So what can we do to use this to increase our lever arm? And then usually a kid will say, you put it on the end. Yeah, exactly. And so then we're like, okay, so with that in mind, how can do you think this one will be better or this one? And I was like, this one. And so,
Go big or go home, huh?
right? And then you get the same guy, and he's comes with really easy, right? And then that's showing the idea that lever arm is just as important as force. When you're talking about torque. And so that's the first. And what we're going to do is we're going to hook it here on both of them, right? And you're going to feel torque because it's pulling it down. And
So keep it parallel to the ground now, don't droop
what
it.
you're trying to do is
Yeah,
keep
don't
it
droop it.
parallel. And so it's okay, so how much harder will it be if we put it on the second notch? Each of these are the same length. And what happens is it actually doubles how much torque you have to apply to keep it up.
Yeah, she's got double the smile.
Doubling the lever.
That's it, huh?
Right?
Yeah.
Lever arm is 2 times torque. So it gets really hard, really fast. So don't be like. See if you can hold through.
Oh, she made it!
It's really hard.
Okay, now I can't really get it.
And so you can see, we usually don't bring these out for most kids. So like smaller kids, you don't give it, but when they're like 6th grade, 5th grade, you can get, some of them get it pretty far.
This is what we start off with when we start talking about, make sure we're at the end, it's about, there you go. This is our temperature
guys can't stay up till
scale,
10
when we
minutes?
start
Let me
talking
guess.
about temperature and states of matter.
That's all right.
And so there are some very important temperatures marked on the scale, which Sharon is about to tell you about.
I sure am. Okay.
Let's bring it down.
Okay, so we have 2 important temperatures right here that I hope you guys know. We have 0 degrees Celsius, which we all know is 32 degrees Fahrenheit. What's that? Water freezes. And
Yeah.
okay. Lower temperatures, water freezes in the ice. And then 100 degrees Celsius is what we know as 212 degrees Fahrenheit. And if it gets any hotter than that, then the water boils. So we use water as an easy example because hopefully they've all seen water in the different states of matter. So like water is ice below 0 degrees Celsius, water is liquid in between 0 and 100 degrees Celsius, and then water as steam boiling away into gas after 100 degrees Celsius. And so then we show that those temperatures that we're familiar with are right here in this little interval. And we brought other temperatures that go all the way down to here, negative 200 degrees Celsius. And that is actually liquid nitrogen. So we brought liquid nitrogen, and nitrogen is what air is mostly made out of. So if you cool it down to negative 200 degrees Celsius, then it actually becomes a liquid instead of the gas air. And then all the way down there is 2000 degrees Celsius. And so that's a huge distance, right? And so that's what this torch is, 2000 degrees Celsius. So it's kind of a dramatic example, like what we're familiar with is just between here and what actually you can have for temperatures like way down there and way down there.
Very good.
So that's what you use that.
You guys are familiar with dry ice, that's only about minus 80. So we brought minus 200 here today, right? We're kicking dry ice's butt. Absolutely. And we're gonna do something with it. You guys hung around, we're gonna make something to eat here. Just in a
Okay,
few
so
minutes.
we look at the really hot temperatures first, and we show that if you heat something up, actually it expands. Well, like the space between the particles gets a little bit bigger, so the material actually expands a little bit. And so we have this demo of this ball and this ring, and right now they don't fit through each other. And then you ask them, if we know that things expand if you heat them up, which one of these should I heat up to have it expand? And hopefully they all go for the ring. If they go for the ball, I do the ring anyways.
And they generally do go for the ring, don't they, guys? Mostly, yeah, mostly. Even the real little kids, they realize they need to make that bigger. But then you ask them what? Can you see it
So
expanding?
you ask them if they can see it expand, and you can't because.
And some of them say yes, though, don't they?
Yeah.
Some of them asked to do these demos. These are 2 demos that they are not allowed to do.
Right, exactly. That's true. That's a good point. There's things they can't do. That's
Okay,
true.
and then you hope that it expanded enough, and it fits through now. Right? The ring expanded, so it fits through.
She said she hoped because one time she didn't eat it. I don't know,
Yeah.
did she?
And then we also have another piece of metal, which is actually made out of 2 different pieces of metal. There's one metal on this side, this is brass, and then there's one metal on this side, this is steel.
And so you heat that up and you ask them to observe what they see happening as it heats. And you see it bending over. And that's because the brass actually expands more than the steel, and so the brass bends over the steel side. And then we move on to our really cold temperature, negative 200 degrees Celsius. And we ask them to predict what they think is going to happen if you cool this down. And a lot of them say it'll go straight. Some of them say nothing. Some of them say it'll bend the other way. And then you actually do it.
If you listen, you can hear boiling, right? Because it's actually boiling. But you put something in there really hot, right? Can you imagine? Yeah, really hot.
I have it this way. See, they never understand that you can just switch it and it's the same. But
You got a red, more red mark on there, don't we? A red
yeah.
mark in there?
So it bent over the other way. I don't remember which way it was bent over. But it's supposed to bend over the other way because the metal contracts more, and so it bends over.
Which one contracts more, Sherry Ann? The brass or the steel?
contracts
Right.
more.
So it both expands more and contracts more, huh?
Yeah.
Both, yeah. Exactly.
Okay, and then we show them a bunch of other things we have inside our magic bottle.
So now Kendall's gonna bring stuff out of there. This is the fun part. Exactly.
Fire is fun. But safety first, always have your safety belt on. You get liquid nitrogen in your eye, you lose your eyes. So it's not a fun thing.
So we just have some normal things in here that we've turned to really, really cool things. So hopefully everyone can identify what this is. Well, what is this? A tennis ball, right? And if you ever picked up a wet tennis ball, it does absorb liquid. So right now, that's liquid nitrogen leaking out from the tennis ball, and instantly it's turning into gas nitrogen. So what do you think happened to this tennis ball when I put it in negative 200 degrees Celsius? What do you think happened to it?
Solid as a rock.
It's pretty frozen. So don't touch that. You will hurt yourself. Now, what do you think happened to this right here? This ping pong ball.
Sherry.
What happened? Nothing really happened to it. It's pretty much exactly the same. It's a really hard plastic and nothing. Do you guys know what this is? So we asked them, this is a really exciting one because what is it? It's a balloon, right? And what is in a balloon? We went through this before. Air, right? We just put this balloon full of gas air into liquid air. So some of that air in there was a liquid. And now it is coming back out into a gas and expanding in all its glory. Right?
Very well put, Kim. Probably a lot of my students didn't realize that. There actually becomes liquid like nitrogen in the bottom of that balloon, right?
Because gas is
exactly.
air is 70% nitrogen,
Absolutely.
right? Now, here's my favorite. I'm going to make sure it's completely frozen. Sometimes it doesn't do what I want it to do.
Yeah, you hold it under for a while.
Yeah.
Hold
So
it
if you
under
guys
for a
actually
while.
realize the
Hold
negative
on.
200 degrees, which is actually 196 degrees Celsius, which is the temperature of liquid nitrogen, is the boiling point of nitrogen.
Yeah,
Just like
absolutely.
100 degrees is the boiling point of water, negative 196 degrees Celsius is the boiling point of nitrogen, right? It's turning from liquid to a gas. It's the definition of boiling point. So right here I have a racquetball, right? What do you think happens when I drop or slightly throw a racquetball?
Slightly throw, yeah.
Don't touch this.
You touched your foot, you're all right though, Chief. You're all right.
Okay, so you heard that, right?
You got the full excitement there.
Now, that was not an explosion, that was an implosion. Because what happens is, this racquetball is made of really, really soft rubber, so it bounces a lot. That's the point of a racquetball. What happens is it freezes completely, and then inside the racquetball, all of the air condenses, just like the air in the balloon, right? So all the air inside is suddenly not exerting that much pressure on the inside of the racquetball. So the outside air is trying to press down on it, right? That 15 pounds per square inch. So what happens is, if you add a little bit of force to it, it implodes. As in, all of the air pressure makes it crack and it implode. And that's where you get that sound.
So what we do is, like, depending on the age, we like to write it down, and I like to have the kids say it with me, like electrostatics, just to let them know, what is it that we're learning and how they can pronounce it.
Or static electricity.
Hey,
What do you guys know about electricity?
you guys want to go to the other one then? We can talk about it a little
There's
bit.
a positive and a negative charge, right? So positive and negatives, they do. What do positive and positive do? Nobody? Positive and positive? Positive and positive would push each other away, and negative and negative. Just kind of like a magnet, just it's a little bit different. So it's actually a.
You know how to say opposites attract?
So we're gonna do static first, or?
Yeah, we have the board.
Yeah, but you can't do it, so you guys go ahead and go straight to the magnets. You guys go straight to the magnets, show the magnets.
So also
Show
our
the
second
magnets.
concept from
And the rest of us guys, let's give a few guys that behind us, getting ready for the other stuff, right?
is electromagnetism. Usually we show them with like little,
Vince, we're gonna scoot.
we start off with like small scale demonstrations, then we move on to a bigger one.
So we all know magnets have a positive and a negative, right? They always have two poles. And so if you grab the magnets, put the magnets,
Not the red bucket?
and the pencil.
Oh, there's these.
Borrow a pen over?
What do you guys need power?
No, something just like this. So basically, so I have one big magnet right here, right? It's actually three little magnets, but just to demonstrate the basics, if you have a magnet, it's always got a positive and a negative, or a north pole and a south pole, not a positive and a negative, like electricity. But so a north pole and a south pole, and every time you break a magnet apart, you break the pole. So this one still has a north pole and a south pole. So you put it back on there, and they stick. You turn it around, they repel each other, right? So that's the basics of magnets. And so what we're going to do is we're going to pull out a big magnet here. And this is actually, these are just simple, regular, magnets. And this is an electromagnet. So to demonstrate the basics of an electromagnet, we'll start off with a battery.
And a small nail with a coil wrapped around it.
And so what happens when you put electricity through the battery here from a positive side and a negative side, it generates an electric current. And so we have a paper clip. And run over everything today. Good thing we practiced. So anyway, it doesn't really work too well because it's not generating enough of a current to go through here. So what we're going to do is we're going to take a ferromagnetic object, which is an object that can become magnetic. So I'm going to stick it through here. Now, I can pick up the safety pin. And so, because what happens is the current, it runs through just like a battery, just like a circuit. It runs through and it generates a current through the coils like this. So then that generates a magnetic field in the opposite direction. So that's what enables it to pick it up. So anyway, so now we're going to use a big electromagnet right here.
Alright, so what we do is that we demonstrate that by getting on a larger scale, more of a coil and more electricity in it, we create a larger magnetic field, and we demonstrate this with the ring jumper.
So this has just a few coils, right? This one has a ton of coils right there. And it's plugged into a wall. So we're probably going to have a little bit of power.
So what happens was that we show them that there's an electric current going through in this direction, the rule of thumb. So what happens is it creates an opposing direction in this opposing direction. And like we learned with the magnets, like poles, they repel each other. That's why the ring jumps up.